Hello, and welcome to Joshi Repair. In front of us we've got an RTX 4090. This is the ROG STRIX Liquid Cooled Edition. Now it's coming for a fairly common problem, whereby it's suffering from memory errors, and we're just going to quickly run through how we diagnose, repair, and finalize this kind of work at Joshi Repair. Jumping right in, we've got the card plugged in, and we're running NVMe to start off with, just to show some of the text that it can provide some inaccurate results. It is rare, but it can do this on some cards with memory errors. So if we just compare that now with mods, where NVMe was showing errors on all banks, mods is showing errors on banks B and D, that is specifically on channels number 1. So let's get right into it and disassemble the card. Most of the time these will suffer memory errors on the banks by the PCIe slot. However, these are on quite uncommon banks. This can be from shipping damage, extremely sticky pads, and even badly binned chips. As you can see, I've quickly labeled those modules for you, so let's get right into the visual inspection. Now, we're looking for any sort of heat damage, heat wear, cracked solder balls that would be under the core, under these modules, any cracked components, that would be capacitors, damaged resistors, anything that looks off. This will give us a better idea on whether we should be replacing the modules or looking elsewhere. It's also a good idea to check the PCIe locking tab area for any cracks. Alright, getting into resistance readings, we're going to start with the 12 volts from the bus. Followed by 3.3 volts aux, and then the 3.3 volts bus. Going up to the top right corner, we are going to be testing the 12 volts from the 12 volts high power connector. That would be both these inductors. Top right is 5 volts, which goes towards powering the LEDs. So far our resistances are looking great. This is just for a reference for us and for future techs. This is our V core inductor, followed by 4 underneath. Next up is our VMEM, so this is for powering up the memory. You're looking at about 40 ohms for micron. Perfect. We've got PEX here, which you're looking at about 50 ohms. Underneath that will be 1.8 volts, followed by another 1.8 volt rail, sometimes referred to as 1.2 volts, which can be on some cards. Our meter a lot of the time has trouble ranging the 1.8 volt rail, so we're actually going to manually arrange that, and you'll see that the top rail ends up reading closer to 750 ohms. Funnily enough, that's what a lot of the Pascal cards used to read. Anyways, we're finally reading the last 12 volts from the PCI bus, which we previously read, followed by 5 volts on the top left. Let's get started. We got our PCB sat on a silicon heat mat, which is set to 200 degrees Celsius. That's left to preheat for about 4 or 5 minutes until the PCB reaches roughly 140-150 degrees on the top. Once sufficiently preheated, we'll then come in with the top hot air with our largest nozzle. This is just an adapter. You can go without a nozzle, but this is a little bit more controlled for us. We'll go in with 100% airflow, starting at 250 degrees Celsius, going up to 300, 350, and maxing out at 375. Once the module has been removed, we'll do a quick inspection to see if there are any burn marks, ripped pads, anything that can tell us what happened here. As you can see, the pads look pretty good, and so we'll get to cleaning. That's by adding some high quality Ursa flux, adding some leaded solder, and then wicking away with some mechanic solder braid. Since there were no ripped pads or signs of damage on the module, or even around it, we likely suspect that it's either a binning issue with these chips or excessive heat when running in applications. Here we're adding a fresh application of flux both to the board and the module, so that there is a correct amount of activation, wetting once the solder melts, and not too much so the module doesn't float around. Following a similar process to how we remove the modules, they are then soldered back on, and once they do reach a liquidous temp of about 220 degrees, as the modules that we use in this case are lead free, that is then held for another 15 to 20 seconds to ensure that all the solder joints are formed, some extra flux is added, and then we let it cool. Rinse and repeat for bank B1, and we're good to go. While B1 is being completed in the background, I will note a few things. So those sheets of aluminium that you can see, the cutouts, they're used for protecting the core and any electrolytic capacitors, even tantalum caps, from excessive heat. Another thing to note is that we do add more flux once the module has melted and soldered to the board to help those joints better form, along with a slight nudge test done at the end to make sure the module is in place. And as you can see, the surface tension does pull it back into place, confirming those joints are making a connection to the board.